Good afternoon. Today I'll be presenting my final progress presentation for AERO4842, where I'll be focusing on a multi-sensor environmental package. Our mission scenario is a landed Europa exploration mission where it is assumed that a probe has drilled through the moon's icy shell and deployed on the subsurface of the ocean. Europa is one of the most promising sites for extraterrestrial habitability, as its ocean may contain what is needed to support life. To assess that, we must understand the local environment. This is done by measuring the temperature, which reveals energy availability, depth and pressure, which defines the environment, and pH and salinity, which demonstrate a chemical balance crucial for sustaining life. My project simulates this investigation on Earth through a multi-sensor environmental package capable of collecting the temperature, level, salinity, and pH all in real time. Next, I'll be going into the apparatus. The apparatus contains a breadboard kit, the DS18B20 water temperature sensor, the LLC4965 water level sensor, and an Arduino Uno. I selected the DS18B20 temperature sensor because it provides high digital precisions with an error of about ½ degree Celsius, and the LL4965 water level sensor due to its analog simple linear response, allowing to simulate immersion depth and detect fluid contact reliably. Continuing with the apparatus, I used a pH probe with a BC interface, an analog conductivity sensor, a plastic Tupperware as a waterproof housing unit, and lots of epoxy and crazy glue. I selected the pH probe to evaluate the habitability data. However, the pH probe failed due to dehydration during shipping, but was still integrated mechanically as part of the design. The conductivity sensor was chosen to measure the salinity through ionic mobility. Next, for the developmental approach. The approach began with wiring and validating each sensor individually. The conductivity sensor and temperature sensor were done simultaneously as salinity is directly related to temperature. They work as an indication of ionic mobility as previously stated and submersible conditions. The water level sensor worked as an immersion detector, which reliably determines when the package makes contact with the liquid. And lastly, the pH sensor was used to determine the acidity and alkalinity of the water if it had been working. The construction of the unit began by using a plastic Tupperware container. Then, holes were measured for each probe respectively and drilled into the bottom surface. Then the surface was sanded to improve the adhesion, as the bottom layer of the Tupperware was a smooth plastic. The probes were then placed into the openings where crazy glue attached them to the unit while epoxy was applied to create a waterproofing seal. This phase revealed several practical engineering challenges. Initially, when drilling, due to the size of the pH probe, many cracks formed around the plastic. To overcome this issue, the plastic was placed on top of a wood beam, and then we drilled directly into the wood through the plastic. The cracks then caused minor leaks, which were fixed using extra epoxy. Then when trying to stabilize each probe, the glue would not attach to the plastic due to its smooth surface. To overcome this, the surface was sanded down and reapplied, which is why it looks a little bit messy in the configuration. Lastly, because of all the extra glue and epoxy, the cap of the pH sensor was stuck to the glue. To overcome this, I heated a steel knife and poked holes into the sides of the probe, allowing water to enter. This was not a viable fix, however, worked as a temporary fix. Once sealed and rewired, the full system was placed on water and integrated for testing. At this point, all available sensors, level, temperature, conductivity were functioning together. The pH probe was present but was not obtaining usable data. Code was done for the pH probe as well, as if it had been working, and results were simulated. Now I will go into a short demonstration of the multi-sensor. So now I'll be going over a brief demonstration of the multi-sensor. So here we have the Arduino IDE set up with all the code, and here we have the apparatus. Some of the products we'll be using is some vinegar to test the pH, and we also have some salt to test the salinity of the water. We filled up our sink with water, with hot water. We should be able to tell the temperature when the sensors are in. So we're going to turn on the serial plotter now, or the IDE. So now it's running. We'll place the tub in the water. It should all be waterproof So then the readings are updating as we go here. As you can see by the readings here, I'm not sure if it captures in the video, we'll now pour some salt in the water and mix it with the spoon. No water is leaking into the housing unit. And then we'll see what the results are. And the salinity has increased drastically already. And then we'll finish off by placing some vinegar in the water as well to see what will happen. But as you can see, the unit is floating well. There is no water leaking into the housing unit, and we were able to get all of our data calculated on the IDE. Done. The results in the table demonstrate how the package responded when placed in water with the changing environments. Key observations include the liquid level immediately increasing from 0 to 60%, confirming the submersion level. The temperature rose from room temperature to close to 50 degrees as it warmed up to the liquid. The conductivity rose sharply as salt was added from about 880 to over 2600 Siemens per centimeter, but then stabilized around 1800 after the salt mixed. And as illustrated, the pH stayed consistent due to invalid readings. These results validate how each sensor would work simultaneously in a mission like monitoring environment. The major source of error which was not adapted was in the pH probe. Despite this issue, the probe is still successfully sealed in the unit, as shown in the figure on the bottom left. The Arduino was capable of handling the load, and the code ran the simulation well. However, for general future projects, I would use a thicker plastic container to avoid cracks, and would sand the bottom layer initially before attempting to attach the probes. This would improve the margin of error and make the apparatus more visually appealing as it looks a little messy. I would also initially purchase a more expensive, reliable pH probe to obtain results. Lastly, while the breadboard is good for prototyping, I would opt to use a printed circuit board as it would be more mission ready. These upgrades would directly increase accuracy, durability, and mission readiness. To conclude, despite many challenges, the integrated system performed well in detecting temperature, salinity, and water level changes in real time, with some exception to pH. And the prototyping highlighted the importance of waterproofing and proper material selection and planetary instrumentation. This work then reflects how a compact, low-power sensor could support scientific goals for future Europa missions by evaluating habitability and environmental gradients. And that is all. Thank you.